Please hold. Assistance is just a moment away.
To join us for the webinar today. My name is Tammy Reller. I am one of the application specialists for Teledyne TechMar, and I am also the Headspace and TOC product line manager. We've had a lot of requests to look at specific and individual methods. Today we're going to take a look at the total organic carbon in source water and drinking water. I'm going to go a little bit through the method in detail. It is an EPA method. It's about 57 pages long, and so there's a lot of information in there. And as most of you know, EPA methods are pretty strict to the guidelines. So there are a few items that we're going to touch on. We're going to talk a little bit about the Fusion TOC analyzer that TechMar has to offer, and we're going to look at some of the samples that we ran in the applications lab. If you have any questions, please feel free to go ahead and type them in, and we will address any questions at the end. We already have, once we go through the slide presentation, I'm going to just pop up the software real quick, because a lot of times that's the number one question, is how easy is it to use the software? So I'll open up the software, and we'll be able to take a look at a couple of the screenshots. And then I will also pull up the application note. There is one already written that goes along with this webinar. So in a couple of days, we will send that application note out to each and every one of you. And then you will also be able to go onto our website at www.teledynetechmar.com, and you can get a copy of the application note or any other application notes that you're interested in, as well as a copy of this audio of the webinar. The audio of the webinar should take about a week, and then that will be up there. So let's go ahead and jump right into this. My slides to change. Oops. So we've talked a little bit about the abstract of the method. So as you know, disinfectants can be added to water to help remove pathogens. But some of these disinfectants, such as chlorine, can react with naturally occurring materials in the water, and they can form these disinfection byproducts, and otherwise known as DBPs. Now, DBPs, they can lead to health problems. So the EPA and this method is all about making sure it's part of the Clean Water Safe Drinking Act, and it's to make sure that we're not getting any of these disinfectant byproducts. So these can be in the form of trihalomethanes, haloacetic acids, bromates, chlorides, and those. So method 415.3 is to be able to gauge the amount of those TOCs, or the disinfectant byproducts, in the water. The two things we're going to focus on today is looking at the initial demonstration of capability and some of the quality control within the method. A summary of the method requires that all organic carbon must be removed or significant error can occur. And this could be biased either false positive or false negative. It can be biased high or biased low based on the way that you calculate TOC, the total organic carbon. And we'll talk about that more in just a couple of minutes. And overall, the organic carbon is going to be oxidized in the sample to produce carbon dioxide. There are two ways of doing this currently. You can do it by a combustion method, or do it by UV persulfate. Combustion is using the combination of high heat, usually 680 to 750 degrees, and a catalyst in order to drive the reaction. Now, for level drinking water analysis, combustion is not always the best way to go, the best technology. So for today, we're going to be talking about the UV persulfate. Once that carbon dioxide is produced, it's measured by a detector. And the detector is usually calibrated with a potassium hydrogen phthalate, HP. And we're going to also talk a little bit more about that. So there's two primary ways that you can measure the CO2. One, using a non-dispersive infrared detector, or NDIR, and a conductivity. So we're going to be talking about the NDIR. Now, in this method, it's fairly flexible. There's several types of systems that you can use. You can use a UV persulfate. You can use a heated UV persulfate. You can use a combustion. So a lot of this is based upon the initial demonstration capabilities, and also meeting the control requirements of the method. So when you're calculating TOC, there's several ways. You take a look at, you'll be able to see my mouse is fairly large and black, and I'll be using this as my pointer throughout the webinar. Several ways that we can measure carbon. All right, so we can look at total carbon is the addition of total organic carbon plus inorganic carbon. We can look at total organic carbon as TC minus IC method. Now, what happens is in this second, when you do TC and IC, you have to do two separate measurements, so it's going to take a little bit longer. And also, now you're increasing the amount of bias that can be in the analysis. So, for all intents and purposes, we're going to purge all of the inorganic carbon, and we said initially that that was one of the requirements of this method, is that you must purge out all of the inorganic carbon in the sample. So essentially, all you have left is the total organic carbon. So in all intents and purposes, the TC is equivalent to TC. The total organic carbon in there is equal to the total amount of carbon. Now, like all of our favorite parts of methods and any methods that we run, we come across a lot of acronyms. So these are not a list of all the acronyms that are used in the method, but it's a highlight of those that we're going to be focusing on today. So your CCC is a continuing calibration check. Your IC is inorganic carbon. IC, initial demonstration of capability. KP, potassium hydrogen phthalate. This is going to be what's used for your calibrations and your continuing calibration check standards. Your laboratory reagent blank. Some next ones. Organic carbon primary dilution standard. And we're going to go into each one of these a little bit more detailed. Or carbon detection limit. Carbon, the quality control sample. Quality control sample is usually a calibration verification standard in a certain range. So it is the known concentration of carbon in it, and is usually purchased from an external source as a way of validating the system. And a little bit about when you have quality control samples out of line or failing, that's a good indicator that you need to either do some instrument maintenance, you may need to do some calibrating. So TC is total carbon, and TOC is total organic carbon. There are several more that you're going to be able, you also have in there laboratory fortified matrix, and LFM, and LFB, a laboratory fortified blank. For the purposes of today, if we went through every single thing in that method, we could be here for a while. So in the interest of time, I'm going to focus primarily on the demonstration of capability and talk a little bit about these standards and what is actually required in this IDC. Separation reminders, and these are very critical when you're going to make up standards for doing TOC analysis. The glassware must be super clean. That's your flask that you're going to make up your standards in. Your vials, you want to use certified 40 ml vials that have less than 10 ppb certified. They're less than 10 ppb of carbon in there. So you want to make sure that everything that you're using is clean, because any extra carbon, even in the air, could be gas lines, anything, could add to extra background within your system. Your organic carbon-free water of less than 10 ppb. Ultra purity nitrogen, If any concentrated samples that are greater than 50 ppm, we're going to dilute them. And when we go into a few of the features of the system, you'll find that the system will automatically be able to tell when there is a sample outside the calibration range, and it will be able to dilute that sample and bring it into the calibration range automatically. Chloride interferences. If I had a nickel for every time I had a question on can I run salt in my samples, and this is a varying question whether or not you're running UV persulfate or combustion. As we know, being the fact with combustion that you're using heat and you're basically oxidizing that entire sample, you have a bit more flexibility with the amount of salt that you have in your samples. These chloride interferences, so if you have salt or anything else in your sample, these are actually going to be competing with the persulfate for the oxidation. So it's end up having not a completely oxidized sample. So in the beginning, when we said that you must remove all of the inorganic carbon, if you have salt in your samples, there's a couple things that you can do. You can increase the persulfate concentration. So if you imagine that you've got your reagent in there and these little chloride ions are all moving around and they're competing for persulfate as well as the sample. So either increase that persulfate concentration, or you may need to use a longer oxidizing time. So you may need to so there are extra steps that you can do. But we want to minimize the amount of salt if possible. You can do that several ways. We can do it by dilution, or you can increase the persulfate concentration or extend the oxidation time. And we're going to talk a little bit more about this. And the reason these can interfere because they can significantly change your results. Initially, if you go ahead and run a sample, and then you go and you change that persulfate concentration or the oxidizing time, you may actually double the amount that you are reading in the detector for that. So it can vary your final results significantly. So we talk about the removal of inorganic carbon and completely purging that out of there. We want the method calls for an IC removal sparging efficiency test. We're going to take a mixture of approximately 100 milligrams per liter. I'm going to show you a table. So this is exactly from the method. As you can see, there are 4 different concentrations or flasks of 1 liter flasks that we're going to have to make up of this. And the reason that we have to make separate stock solutions is if we make these all up in a single liter, they would not be mixable with one another. So you have to make them up in 4 separate stock solutions. And then we're going to take just a small amount from each one and add it to a 40 ml vial. The idea behind this is we want to make sure that we're sparging long enough in order to remove all of that inorganic carbon, because it could bias our results high or low. We want that as low as possible, and you'll see. So if we take each of these compounds and we make up a flask A, B, C, and D, and are straight from the method. And the reason that if you add all of these in and make up a 1 liter flask, it actually comes to 102.5 milligrams per liter. So roughly around 100 milligrams per liter. And the reason that they do this is that they wanted to be able for the analysts to simulate the most extreme inorganic carbon concentration possible. So this is the first thing that we were going to do. This is part of the IDC. So we're going to take, after we make up each of these concentrations, we're going to 10 mils of A, 10 mils of B, 10 mils of C, and 10 mils of D, and we're going to add each of these to a 40 ml vial. Now, when you shake that vial, you're going to find out that that solution might be a little bit turbid and cloudy looking. So we're going to get 40 microliters and either use phosphoric acid, hydrochloric acid, sulfuric acid for each one of these. The solution that we need to make up for the study that we are running is the organic carbon primary dilution standard. This is essentially a stock standard that we will be working from. To make our calibration curve from this stock standard, you can make many of your continuing calibration checks from this stock standard. This is directly from the method, so you can, it'll be in the application note, or you can go and read it directly, and we made it exactly the same. So we diluted 1.063 grams of the potassium hydrogen phthalate, fill of phosphoric acid to a liter of deionized water, and that gives us a final concentration of about 500 ppm of organic carbon. This is usually good for about 6 to 12 months if stored in an amber bottle. No refrigeration is required on this. We're going to go ahead and we're going to make our calibration curve from this. Now, later on, you run your quality control sample. And if you remember, the quality control sample is a known standard with a known concentration that is just like all of your samples and usually purchased from an external source. If your quality control standard fails, that is one of the indicators that you may want to go back and recalibrate your system. Time for a new calibration. As long as that continues to pass, and it also depends on your SOP. Even though it says that you know, as long as your QCS is passing, their calibration is fine. Each individual laboratory may have their own standard operating procedure that says, nope, we must calibrate once a month and run these particular standards. Or it may be a municipality that says, you know, we have to run compliance samples once a month. And every time that we run that compliance sample, we have to calibrate. So it really depends on your SOP as well. So the OCCAL is the organic carbon calibration. Usually you have to run a minimum of 4 points on the calibration curve plus a calibration blank. The calibration blank is always the first one that is run. That is essentially what is supposed to be equivalent to reagent water. And it has to be treated as same as all the calibration standards. So when you make up your standard, you keep your calibration blank with it, and you run this initially. It has to be less than 0.35 milligrams per liter TOC. This is usually good for 30 days if stored in amber glass or in dark glass. For this note, we ran a total of 7 points. We ran 6 points for our calibration curve plus the calibration blank. IDC requirements in the method are, first you have to do an initial demonstration of low system background. So you want to make sure basically that the system is very clean. Your reagent blank must come back less than 0.5 ppm of organic carbon. Do an initial instrument calibration verification. This is where we're going to run that independent quality control sample. We're talking more of drinking water and source waters, and we're looking more at lower levels. For this paper, we ran a calibration range of 0.5 ppm to 25 ppm. So your independent quality control sample has to be between 1 and 5 ppm, and it must be within plus or minus 20% of its true value. Organic carbon flow injection memory, this is where we're going to run a lab reagent blank, a highest calibration point. So we want to make sure that after our highest calibration, which was 25 ppm for this paper, that we have our blank comes back at less than 0.35 ppm. If in some cases in the method, if you are getting close to that and you have higher level samples, you'll either want to have those samples diluted and put back into that calibration range, or you may be required to run a blank after the high samples. The test, the IC removal sparging efficiency test. That's where we took and we made up the IC test solution, and it must be less than 0.35. So the first thing we're going to do is we make those 4 flasks, and we want to make sure that we're removing all of the inorganic carbon sample. So we took the test solution and we're going to run that as a sample and make sure that sparging is long enough in order for that number to be less than 0.35 ppm. We're going to get the demonstration of accuracy. We're going to look at precision, and also going to look at the organic carbon detection limit determination. So the instrument that we used for this application note is our TOC Fusion Analyzer. It's a UV Persulfate. My pointer here. This is the instrument, a view of it. This is the sampler up top that can run 75 positions for 40 Malvoa vials. You can see in the center these 4 125 ml stock solution positions. When we go in and look at making the calibration curve, one advantage is that the system will auto-calibrate for you. This is a quick snapshot of the instrument with the front cover off. So over to the left here is our halogen scrubber, and this, because we're measuring CO2, the detector, everything can be affected by halogens. So to prevent any analytical errors, the halogen scrubber helps to remove any chlorine and other halogens from the carbon dioxide before it enters the detector. This is our UV oxidation reactor. So this is where the sulfate combined with the UV light is going to oxidize all the carbon in the sample. It is a syringe and valve mechanism so that we are able to do automatic dilutions within the system. And it has a volume delivery range of 125 microliters all the way up to 25 ml. To the right, I apologize, my mouse keeps going away. Right here, this little glass bulb apparatus is the moisture control system, and over here is our IC sparger, and this is going to hold the sample while we're purging the inorganic carbon out of the sample, getting it ready for analysis. And the addition of the acid, the purge gas is going to flow through the sparger and remove all that inorganic carbon. A couple features that I'd like to point out in this are the mass flow controller, static pressure concentration, which is a little bit different than for those of you that had the previous Phoenix, where we used a flow-through detection scheme. We're going to talk a little bit about auto-calibration and IntelliDilution. So the calibration is very beneficial. It helps to minimize any error from making your standards manually. It can also reduce the amount of time that you spend making standards. It uses a single stock solution, and you can either make this yourself, as we did earlier. We made a stock solution of 500 ppm KHP, or you can buy pre-made, you purchase them already made. Automatically going to dilute to the final volume, and that's all based upon, in the software, we would set up a method with our calibration points and the dilution factor for each of those. So if we go back to center here, this is where you can put it can automatically dilute from any position within the center here, which are your stock solutions, or also dilute from actually one of the vials as well. Solution is kind of the smart or the brains of the system to see if a sample is over range. So we talked about earlier that if you have samples, since this is a low-level analysis, if you have samples around the 50 ppm range, you may want to have them diluted to back into your calibration range, which for this paper is 0.5 to 25. So the system automatically be able to tell, okay, I've got a sample that is now 50, let's say 50 ppm, and I'm going to do 1 to 10 dilution on that. I need to do 1 to 10 dilution in order to bring that back into the center of the calibration range. So different things that you can set up in the software. You can say, all right, go ahead and automatically dilute it and get it back into the calibration range. And it'll try it up to 3 times. So you instruct the system what to do and how you want to handle samples that are highly concentrated. So about auto-calibration a little bit and IntelliDilution. So I just wanted to show this picture more. This is the actual NDI detector down here in the bottom. And this over here is your mass flow controller. The advantage of the mass flow controller is that you can control the flow in mode operations. So if I want to decrease the amount of time that it takes to run a single sample or a single replicate, I want to be able to increase my sparging flow. So, or it can give me, I want to increase the flow as I'm cleaning up the system. It can help with cleaning up as well. So it gives you the flexibility to adjust the flows as you need them based upon individual applications. And the thing is the static pressure concentration. Before we have most NDIR detectors use a flow-through technology. This is where it's going to pressurize that sample. So as the sample is coming off and you've got CO2 gas now going into the NDIR detector, it's going to close off that valve and it's going to pressurize that sample and it's going to take a single reading. This is so that we can get an increased sensitivity and precision because we are measuring the entire the oxidation of the products of that sample in one reading. So the output of that signal is proportional to the concentration of CO2 in the carrier gas. All I really wanted to talk a little bit, I just wanted to give you an overview so you have an idea, if some of you haven't ever seen diffusion, to get an idea of the instrumentation that we used to run this analysis. So back a few slides ago, we made a 500 pp standard by adding 1.063 grams of AHP and some phosphoric acid and made a 500 ppm standard. In order to make our calibration curves, since we're running a fairly low curve, we want to do a 1 to 10 dilution of that. So we started with a 50 ppm stock standard and said we need to run a calibration blank, and this calibration blank first sample has to be less than 0.5 ppm. Then, as I set it up, that I want to pull all of my calibration curves from position A in the center of my tray, which is 50 ppm. And it automatically do a 1 to 100, 1 to 50, 1 to 25. I was able to select all of these in the software in my calibration method for concentration of 0.5, 1, 2, 5, 10, and 25 ppm TOC. Calibration, this is not part of the IDC requirements, but it's not the instrument demonstration capability requirements, but it's actually a requirement of the method when you get more into the quality control. We always run a curve, and we always are looking for an R-squared value. So in this case, it's 0.930 is what it requires. For better results, it would be 0.9950 or better. I apologize for that typo. And our result was 0.99992. So our curve is very linear. So on the initial demonstration of capability is to show that we had low system background. So we ran a blank water sample, and the requirement was less than 0.35, and our results were 0.068. So well within that limit. The second thing that we need is the instrument calibration verification. You have to run an independent quality control sample that's in the range of 1 to 5 ppm. We run a 2.5 ppm organic carbon standard. You have within plus or minus 20% of this 2.5 ppm. We received a 2.63, so we're plus or minus 5% of the true value. The carbon flow injection memory. After the highest calibration point, which was 25 ppm, we run a laboratory reagent blank. That requires less than 0.35 ppm. Our results were 0.126. The inner carbon removal sparging efficiency test. So we made that extreme IC sample, which is approximately 100 ppm of inorganic carbon. And when you test mix, it has to be less than 0.35 ppm, and our result was 0.245. Now, the detection limits, you have to run N equals 7. So 7 samples, and you have to run them over a consistent period over 3 days. And usually you run them in the range of 0.1 to 0.5. Depend upon what the lower detection limit range of your SOP is. So for case, we were running 0.5 to 25 ppm, so we ran a 0.5 ppm organic carbon. So the requirement is that it has to be greater than 0.35 ppm, and our result was 0.034 ppm. Look at the accuracy. We have 5 separate samples, and you have to run those between 1 and 5 ppm. We ran again in the center of that range, around 2.5 ppm, and it must be within plus or minus 20% that true value. Our result was 2.6, which gives us an RSD within 2.17% of the true value, and at least our demonstration of precision. So you take the same 5 samples that you ran for your accuracy at 2.5 ppm, and percent RSD must be less than 20%, and ours was 0.44. So all of these look at the overall method. We primarily looked at all the major parts of the initial demonstration capability. Now, we have to run the IDC usually when you're changing over to new analysts, or it's not something that most people have to run all the time, but it really does give an overall view of how the instrument is running as well. So we met all of our IDC IDC requirements. And you run these prior to running samples. Now, you get into the rest of the method, there's a lot of other quality controls that you'll be running. So once you pass all of these IDC requirements, now you know that the instrument, that you're ready to go, that you're able to move forward with running your samples. You're going to be running clean blanks. You're going to be running lab reagent blanks. You're going to be running lab duplicates, fortified matrix. So there's you're going to continuing calibration checks. So continuing calibration check, usually before you go to run any samples, you have to run a continuing calibration check at the low level. So it has to be somewhere below 0.7 ppm, I think it is. So if we ran around 0.5 on our curve, you're going to run a continuing calibration check at 0.5 ppm. And that has to be within plus or minus, low end has to be within plus or minus 50% of the true value. Now, you also will run a medium calibration check, and after 10 samples, for the 10th sample, you need to run a continuing calibration check as well. That needs to be plus or minus 20%. I think the majority run either a low-level calibration, which has to be in the front of all your samples, and medium continuing calibration somewhere without through of your analysis batch. An analysis batch consists of 24 hours and is no more than actual 20 samples, including all your calibrations or your standards. So I'm going to just hop out of this. I'll leave this, I can bring this back up in a minute, but I just want to take you out of the slide presentation and show you a little bit about the software and how to manipulate through that. So this is going to be difficult. A little bit of my slide down, so I apologize. So this, as you can see, it is all Windows-based. It runs on Windows XP or higher. If we want to open a new calibration, a new method, or a new schedule, so I'll show you what so I have a method open here. So we go File, New Method. And see, when you go to open a new method, you can pick IC, TC, TC minus IC, or TOC. It gives you those options. So just grab. Me now, I can pick, there's a drinking water, pharmaceutical water, or wastewater. So let's say we're going to do a drinking water. This is our sample volume that we're going to pull for each replicate, whether or not we're going to do any dilution on that sample. So each one of these, when you click on this, tell you over here, the dilution ratio to be applied per sample. First time, the amount of time between adding reagent to the time and starting to sparge the sample. You can program all of these in, or these are already default methods, and it tells you the optimal sample range up here for this method. So 0.0027, so essentially 0.3 ppb to 15. 2.7 ppm to 15. It's a little difficult to read on here. Apologize. You had a schedule. I had one up here already made earlier. This is an example of a schedule. We're running first a reagent blank. And here's where I wanted to, and it automatically put this in because I used a TOC drinking water calibration method. And it's going to pull everything out of this position A. So in this analysis, we had a 50 ppm standard in this position A, which is the center of the carousel ring, and it's going to pull out the appropriate concentrations. So it knows that it needs to do a 100 dilution in order to give me a 0.5 ppm here. It needs to do a 1 to 50, or a dilution to give me a 1 ppm standard, and so on. So you want to look at this is an instrument configuration. It's just an overall. It can connect via RS-232 or Ethernet. The configuration enables me to choose. So the standard is 75 vials, which uses the 40 ml VOA vials. But there are separate carousels also for 55 ml vials and for 20 ml vials. So tools there's different tools. The biggest thing I want to show you is diagnostics. So if some reason you were having any issues with the instrumentation or something just didn't seem right, the first thing that we would do is have you go to this diagnostic section, and it enables you to control all of the mechanical items within the instrument. So the first one is your valves and flows. The second one is your syringe and pumper. And of course, I don't have an instrument connected to this right now. If I wanted to go and see, all right, I wanted to make sure that the syringe was pulling acid, I would click on this, and it would automatically go to this, and it would pull an aliquot of acid into the syringe, and you can see what's happening at all times. So if we want to test, where the arm's going, or we want to test the carousel, or if the needle position is for some reason off. So the first thing that any tech support will do is to try to help you get up and running as fast as possible. And this benchmark enables you to do that. And we have this in all of our systems now. And it just enables you to quickly go in and test the mechanicals of the instrument. You also have leak test or leak checking available with each of these. And because you have a mass flow controller in there, it validates the system it takes the pressure of each of those samples. So you're able to pull that up out of this. You're able to pull that up in a system history log. All right. So if I go in, and it'll keep track of just about everything from the time that you change a password, and it often asks you, because this is 21 CFR compliant. If it asks you, to go in and see if somebody has changed many changes to the method, and they have to give a reason for changing that method. So there's a very accurate history log kept. They can go in and filter and say, I just want to see the errors. And unfortunately, I'm not hooked to an instrument, so I won't really be able to show you anything. But you can go in and say, I want all the information, and I can separate it out by a date range. So for some reason, if it's starting in the middle of the night or what have you, first thing I would do is go to my history log, say, okay, what happened? All right, it ran these samples, and then, experienced something here there in between. Very helpful as well. The menu, these are help files that we put in that are clips and excerpts from the user manual that enable you to get information quickly. So look at the contents and go to this is where I can quickly go and say, well, how to go in and change my password. And it's going to give you, all right, you need to click on Tools, Change Password from this main screen. And it'll take you through the step-by-step instructions that are just a click away. We're doing analysis, and we want to know how to go in and create a new schedule. I can now click on that and keep giving me the links on how to go in and create that schedule. Also over here on the right side of the screen, this gives you what's going on with the unit at all times. So you get the sample that it's running, what the calibration is, what the method is. You know, how many replicates am I running for each of these samples? It's telling me what my blast flow controller is, what I'm setting it to, and what the actual is. When your sample goes into the IR detector, it's going to be pressurized at 50 psi. So you want to make sure that your set point and your actual are at 50 psi for that detection. It's going to give me a pressure reading, so it's going to give me that it's enabled to do almost like a leak check on each and every sample to ensure you know, there's no leaks or anything in there that would give us you know, possibly a false result. The reports can give you get all the information as metadata in the reports. You can export that to an Excel spreadsheet or to Excel file or a CSV file. A lot of times, if you are calling into us and we are helping you try to improve your methodology or optimize your parameters, we'll have you just send that, export it over to a file, which you're currently doing, and email it to us, and then we'll be able to take a look at it and say, all right, maybe we can make some adjustments here or there depending upon the application. So I'm going to keep this up. If you have any questions, if you could please send into, that concludes our webinar for today. If you have any questions, please feel free to go to our website. It has a plethora of information and application notes on all of our products at www.teledynetechmar.com. You can email our tech support group at teledyne.com for any additional questions you might have. There's also an 800 number there for anyone within the United States, and then the other phone number is for anyone outside